Hey everyone, welcome back. Features are the way you represent your knowledge about the world for the classifier. And today, I'll walk you through techniques you can use to represent your features and utilities TensorFlow provides to help. We'll use a dataset from the US Census as an example. And the goal is to predict if someone's income is greater than $50,000 based on attributes like their age and occupation. The dataset is stored as a CSV file, and previously we've seen how to use the column values directly as features. But today we'll use feature engineering to transform them into a more useful representation. As we go, I'll visualize what these transformations do using a tool called Facets, and you can find a link to it in the description. You'll also find complete code to train a TensorFlow estimator on this dataset. Okay, let's get started. Let's begin with a numeric attribute like age and think about how we can use it to predict income. Now, if you think about how age correlates with income, our first intuition is that as age increases, usually so does income. And the simplest way to represent this would just be to take the raw numeric value and use that as a feature. Here we're building a list of features we use to train the model, and each of these is stored as a feature column. This contains data about the column from the CSV file and how to represent it. Here we'll write a feature that just uses the raw value of age, and this string corresponds to a column in the CSV file. Now, what can go wrong with this approach? Well, if we think more closely about age, we realize it's not in a linear relationship with income. The curve might look something like this. It's flat for children, then increases during working age, and decreases during retirement. A linear classifier, for example, is unable to capture this relationship. That's because it learns a single weight for each feature. To make it easier for the classifier, one thing we can do is bucket the feature. And bucketing transforms a numeric feature into several categorical ones, based on the range it falls into. And each of these new features indicate whether a person's age falls into that range. And now a linear model can capture the relationship by learning different weights for each bucket. Let's see how this looks in Facets. Conveniently, there's a live demo that runs in the browser with our census data preloaded. And each individual from the CSV is visualized as a dot, colored by income. If you click on a dot, you can see stats about the person. Now let's bucket by age, and you can adjust the number of buckets to make it more or less granular. How you choose the number of buckets is up to you, and ideally you'd want to use your knowledge of the problem to do this well. In TensorFlow, we can create a bucketized feature by wrapping a numeric column from the CSV. And here we're specifying the number and the ranges of the buckets we'd like created. Once this is done, we can add the bucketized feature to the list used to train our model. Now let's see how to represent a categorical feature, and I'll use the education column as an example. Because there are only a few values, the best way to represent this is just to use the raw value. And here we'll create a feature column that says education can be a single value from this list. Of course, you could also read the values from a file on disk rather than writing them out in code. Now, using the raw value is the right thing to do when there are only a small number of possibilities. We'll cover the case where there are thousands of possibilities in a moment. First, let's take a look at feature crossing. Feature crossing is a way to create new features that are combinations of existing ones. And these can be especially helpful to linear classifiers, which can't model interactions between features. Here's what this looks like in Facets. I'll take our age buckets from before and cross them with education. Under the hood, you can think of a true-false feature being created for each bucket that tells the classifier whether an individual falls into that range. Now, these buckets can be informative, and here we see some groups are likely to have a high income and others low. In code, using a feature cross works the same way as before. We'll cross our age buckets with education and add it to the list of features to use. A feature cross can generate many possibilities quickly, which is why they're often represented under the hood with a hash. A hashed feature column is one way to efficiently represent a categorical feature with a large vocabulary. More importantly, you can use these as a way to make your data easier to work with because they free you from having to provide a vocabulary list. In this example, we'll represent the occupation column from our CSV file by using a hash with 1,000 possible values. Notice we don't have to provide a vocabulary list. And to avoid collisions, I've set the hash size so it's larger than the number of items in the vocabulary. Here's how this works under the hood. Normally, a categorical feature is represented as a one-hot encoding. That means there's one bit for each possible value in the vocabulary. And we can create a lookup because we know the vocabulary list in advance. Now, if we don't know the vocab, we can use a hash function to compute the bit automatically. The downside is there could be collisions, meaning different items are mapped to the same value. Hashes can also be used to limit memory usage at the cost of adding some noise to your training data. If you have a large vocabulary, it can be memory intensive to use that as input to a neural network. A hashed column can be used to limit the maximum number of possibilities, but I prefer them simply as a tool to save you programming time. Finally, I'd like to mention embeddings, and these can be less intuitive than the other techniques, but they're a powerful way to work with categorical data in a deep learning setting. You can think of an embedding as a vector that represents the meaning of a word. And we can visualize a data set of word embeddings using the TensorFlow embedding projector, and there's an online demo you can find in the description. Here we're looking at a data set of 10,000 words, each of which is represented by a vector with many dimensions, projected down to 3D so we can see them. You can search for words in the box to the right, and if you experiment a bit, you'll find similar words are often close together. For example, all of the words in this cluster are cities. What's neat about embeddings is that they're learned automatically in the process of training a DNN, and to make that happen, all you need to do is write an embedding column. Here we'll create an embedding for education with 10 dimensions. Now, embeddings are helpful if you have a categorical column with a large vocabulary and you want to compress the representation, so the classifier learns general concepts rather than memorizing the meaning of specific words. For example, imagine if the census data had a column called job title. There are thousands of different jobs, and an embedding could be used to help your classifier learn that words like programmer and software engineer often mean the same thing. Okay, I hope this was a helpful intro. And thinking about how to represent your features is one of the most important contributions you can make to a machine learning experiment. Feature columns are great because they let you experiment with different representations in code and make advanced features like embeddings accessible. As a next step, I'd recommend you try the code in the description and see if you can modify it for a problem you care about. Thanks for watching, everyone, and I'll see you next time.